In this lesson, we're going to look at trig identities. So the first thing we're going to focus on are our well-known identities, and then we're going to use these to prove other more complex identities. So when we're looking at this, we have three types that are most common, and those are the reciprocal identities, quotient identities, and the Pythagorean identities. So this set of three here are going to be your most important. So when you take a look, sine, cosine, and tangent, the U just stands for an angle. When we're talking about sine, that's the same thing as 1 over cosecant. Cosine is the same thing as 1 over secant, and tan is the same thing as 1 over cotan. So these bottom three trig functions are cosecant, secant, and cotangent. So when you're looking at these, the next set, it's basically just flipping these. So see how cosecant is the same thing as 1 over sine, secant is the same thing as 1 over cosine, cotangent is the same thing as 1 over tan. So they basically just flipped. Those are the reciprocal identities. Quotient identities, if we have tangent, it's the same thing as sine over cosine. When we're looking at cotangent, if you look up top here, cotangent's the same thing as 1 over tangent. So essentially what that means is 1 divided by sine over cosine. So if you have 1 over sine divided by cosine, keep change flip to actually go through with the division, ends up giving you cosine over sine. And then the Pythagorean identities, the one that shows up a lot is this one here. Sine squared plus cosine squared equals 1. So anytime you see a sine squared and a cosine squared, a lot of times you're going to be using this. So just be aware that if you see it, think about the Pythagorean identity as a possibility. So basically, these identities are almost like formulas or theorems that someone has proven, and we can just use them at this point to simplify trig expressions or to prove other identities. The last two Pythagorean identities are also important ones that show up, but not as often as sine squared plus cosine squared equals 1. These last two I wouldn't really worry too much about, but I just wanted to include them because they are other identities, but I don't see them happening that often. So it's really the top half of this page. So let's look at some examples of how we actually use these. So the first thing is going to be simplifying trig expressions using these identities. So if you're given some type of expression, sine, so for example, sine theta times cotan theta, we want to rewrite this, or we want to simplify it so that it's only containing a single trig function or a constant. So what that means is I need to make this so that it's only one trig function. So first thing is I know cotan. Cotan is either 1 over tan or cosine over sine. Um, the identity that you want to use here is not going to be 1 over tan, but it's going to be cotan equal to cosine theta over sine theta. And the reason why I choose this is because since I have a sine in here, it's going to be convenient for me to choose the identity from the previous page that has a sine in it. I don't want to use 1 over tan because that's not going to help me eliminate anything. So off to the side here, I'm just going to write my identity so you can see what formulas I'm using from that previous page. So since I know cotan is equal to this, I'm going to rewrite sine of theta, and instead of writing cotan, I'm going to replace it with what it's equal to. So cosine theta over sine theta. And then since sine theta is really over 1, that allows me to cancel these because it's sine theta divided by sine theta, which is just 1. And I'm left with just cosine of theta. So that's as far as you can go with it. That's what it's asked us to do, is get it into a single function, and that is a single trig function, cosine of theta. So let's look at some other examples. This one here, sine theta and secant theta. I can't do anything with sine theta by itself. So what I do is I look at what does secant translate into, or what's another thing that I could use for secant. So if I go back to that previous page, I look and I want to find something that I could use for secant. So I have this one, and that's really it. I also see secant here, but that's really not going to be helpful. So when I look through these, I have secant squared, but I can't do secant squared from a secant. So really the only identity I have to use for secant is going to be this one right here. Sine, I could have changed to this, but really, honestly, I wouldn't worry about changing sine and cosine or tangent. I would worry more about if you see cosecant, secant, or cotangent. Those are the ones that I would change into sine, cosine, or tangent. That's usually the best way to go about this. So I know secant is equal to 1 over cosine. And what I do over here is I go ahead and I keep the sign, and instead of secant, I replace it with what it's equal to. Okay? And this time I can't cross anything off, but if I put this over 1 and I multiply these, I end up with sine theta over cosine theta. And then what ends up happening when you see this, hopefully you're starting to see something that it could equal. But if you're not sure, if you look back, look at sine over cosine, and I see it right here. So sine divided by cosine is really the same thing as tangent. So that allows me to use that identity. So I'm just going to write it over here because this is like my list of identities I'm using. So instead of having sine over cosine, I can replace it with tangent of theta. And then there we go. I have it as a single trig function. All right, so looking at the next one here, cosecant and 1 minus cosecant squared, or 1 minus cosine squared. So first thing is, whenever you see a cosine squared, you want to be thinking of that Pythagorean identity. You really want to think of this identity because you're pretty much always going to be using that whenever you have a sine or cosine squared. So the question is, how do I get this identity to look like this? So the answer to that is by subtracting cosine squared theta from both sides. That will leave me with sine squared theta equaling 1 minus cosine squared theta. So since this is an identity, you're allowed to manipulate it and solve it and get one variable by itself however you need to, because it's already proven to be true. It's something that we can just accept it's true, and we can rearrange it however we need to. So now that I have this, I can use this as my identity, and instead of having 1 minus cosine squared, what I can do is I'm just going to keep this cosecant for right now, and I can replace this with sine squared theta because that's what that's equal to. And now when I look at this, I still have two different trig functions, so I need to replace one of these other things. So right away I see cosecant as something that I should replace, and cosecant is equal to 1 over sine. So that means I can replace this with 1 over sine. And then I can keep this. And now this is really like being over 1. Sine squared theta is really like saying sine times sine, sine theta times sine theta. So this means there's 2 up top and there's 1 at the bottom. So basically this is really like this, sine theta times sine theta on top over sine theta. So a sine theta divided by sine theta is a 1, and we would be left with a sine theta. So that's it for that one. So really just knowing these identities will help you figure out how to go about this whole solving process. So just keep that in mind when you're doing these, is you really want to look at what do you have and what can you replace it with, and that'll help you get down to a single trig function. Looking at the next page, we're going to do a little bit different. Instead of just simplifying the expression, we're going to actually work on proving this equation to really make sure that this is really true. Because right now, I could put a question mark there. Does the left-hand side equal the right-hand side? So when you're doing this process, you don't really know if this is an equation yet. So you can't move one thing to the other side. I can't move things back and forth. I have to simplify the left-hand side and then simplify the right-hand side, or vice versa, or work on one side at a time. So you can't move, I can't like subtract cosine squared from one side to the other, because that would be assuming that it is an equation, because whatever you do to one side of the equation, you have to do to the other, but we don't know that it's an equation. We don't know that it's truly equal yet. We're trying to prove that it's equal. So when it's proven, then you're allowed to manipulate it however you want and move things around, but until then, you can't. So let's just make a note of that. For these identity proofs, you can only work on one side of the equation. One side of the equation. I'm going to put equation in quotes because it's not really an equation. We're calling it an equation because there's an equal sign there, but it's not really equals yet until we prove it. So I'm going to do the same process where I'm going to list off the identities as I use them so you know where I'm getting things from. So the first thing I see here is I see sine and I see cosine squared. Sine squared plus cosine squared. Right away that one stands out as a really common one. I know that the sum of those is equal to 1. So I'm going to just list that off to the side here as that's my identity that I'm using. So I'm just going to list it. So right now I am working to simplify to show that this is equal. I don't know that it's equal. So simply what that means is I'm just going to kind of carry down this secant along the way. I'm not going to touch that. I'm trying to get basically the left-hand side to equal secant squared. So I'm going to just rewrite this as tan squared theta plus 1. And I'm trying to see if that'll equal the secant squared. So I see a tan squared of theta plus 1. So that tells me that I want to use that Pythagorean identity for tan. So the tangent Pythagorean identity is tan squared theta plus 1 is equal to secant squared theta, which at this stage, I have tan squared theta plus 1. I know that that's equal to secant squared theta from the previous page. So I have to see, does that equal the right-hand side of the expression? Well, yes, it does, because the right-hand side is just secant squared theta. So yes, it does check out and it proves. So again, you're working on one side at a time to see if you can get it to equal the other side. You're allowed to simplify either side of the expression. I usually start with the side that's already expanded and try to condense it to equal the other side. But you're allowed to work from one side, go work to the right side, and then come back to the left side. That's totally fine, but you just have to make sure that you're not moving things and you're just simplifying one side at a time. So for this next one here, the first thing I automatically want to do is I see a secant. And secants to me mean that I should be switching this up to match more of what I see in the expression, or more of what I see in the equation here. And I see cosines and I see sines. So that tells me that I should get rid of the secant and turn it into its reciprocal function. So secant is the same thing as 1 over cosine theta. I always remember secant too as it looks like cosine backwards. So CE or SEC, if you look at it backwards, CES, if you just pretend that's an O, is like cosine. That's how I remember that that one's cosine. So then what this allows me to do is I can write cosine theta. I can replace secant with 1 over cosine. And then I'm just going to keep everything else. And then the right hand side here, I'm really just going to kind of carry it down. So I'm just carrying this along the way. So now once I see these parentheses, that means I want to distribute. So you're just treating it like a regular expression. So cosine over cosine, because this is cosine on top and then cosine on the bottom. When you multiply, it's just going to be 1, because these cancel. And then minus cosine times cosine is cosine squared theta. Notice the squared is next to the cosine because it's cosine times cosine. The squared isn't next to the angle because that would mean that you're squaring the angle, and you want to actually square the trig function. You want to multiply the trig function by itself. So now that I see a cosine squared, this tells me that I probably want to be using my Pythagorean identity, make sure you have the angles too. Make sure you always write cosine or sine of some variable. So if I can rearrange this to look like this, then we're in good shape. So if I subtract cosine squared theta from both sides, that will allow me to have 1 minus cosine squared theta, which instead of having this, I can replace it with sine squared. So sine squared theta, and if you just carry this down, there's your sine squared theta, it checks out and it works. This is a true statement or an identity. Alright, so let's look at some other ones here. So I look at this one right away, I see cotan is something that I probably should replace, since cotan is one of those reciprocal functions or quotient function. So cotan of theta, you could write it as 1 over tan, or you can write it as cosine over sine. The way to go here is going to be cosine over sine. The reason why I know that is because I have sine and cosine also in the function. So turning things into all sine and cosine will hopefully allow me to cancel some things. So I'm going to just rewrite this, sine theta. This is going to be cosine theta over sine theta. And now what happens is these cancel. So this is like over 1. So I'm left with cosine theta over 1, which is just cosine theta. So if I bring this down, I end up with what I needed. The left-hand side equals a right-hand side. Just be aware too, when you're doing these proofs, you might go through this process and you might plug in the wrong thing and it doesn't work out, so you just have to try it again. That's the thing with these, is sometimes they're not as straightforward, where you might not get it right on the first try. You have to try some different identities, because if there's multiple things to plug in, you don't really know until you try it which one's going to work. Sometimes both methods will work, or multiple things will work. Other times it becomes too difficult to try to figure out algebraically if something works, so you would just try something else. So just don't be afraid to try different things here and plug in when you're doing these. So for this one, I see a sine squared. So right away, as soon as I see a sine squared or cosine squared, I think about that Pythagorean identity. And I think about how can I use that. So when I look at this, everything else is in terms of cosine. So I have cosine and cosine and a sine squared. So that tells me if I can rewrite that sine squared theta with cosines, I'll be in better shape. So what that means is I'm going to subtract cosine theta from both sides. That way I can get sine squared by itself. And that will allow me to replace this sine squared with 1 minus cosine squared. And then it gets me everything in terms of cosine, which is a good thing. So I have 1 minus cosine squared theta over 1 minus cosine theta. And again, remember, you're just going to be carrying this along. You're trying to see if the left-hand side equals the right-hand side. So now, when you see this top part, we have to somehow be able to get this down to cancel out the 1 minus cosine theta so that we can end up with a 1 plus cosine theta. So here's what I would suggest. Since I have this 1 minus something squared, so let's pretend for a second it's 1 minus x squared. If you wanted to cancel 1 minus x squared with a 1 minus x, what you would end up doing is you would factor the top, which ends up being a difference of perfect squares, because 1's a perfect square and so is x squared. So you take the square root of each piece, you switch the signs, 1 positive, 1 negative, take the square root of the second piece, you end up with this. And then on the bottom, you had 1 minus x, pretending that x is my cosine. Those cancel, and I'm then left with a 1 plus x, which is exactly what I need. So instead of doing it with x's, let's do it with the cosine acting as like my x, or my variable. So this is the difference of perfect squares, so I have 1 plus cosine theta, and then 1 minus cosine theta, because I'm taking the square root, doing plus or minus in between. I keep the bottom. And then what happens is these cancel, and I'm left with 1 plus cosine theta, carrying this bottom part down all the way. We have 1 plus cosine theta, so this checks out and it works. It's an identity. So let's look at just a few more of these. Just again, more practice with these, the better. But keep in mind, there's going to be times you get through a problem, and then there's going to be times where you get stuck in between, and you might have to start over. It's what happens with these. So these last couple are probably the most complex you'll see. And it's really just because they have fractions, so they get a little bit messier. So when I look at this one to start, right away I want to think about how I can convert this so that I'm getting things in terms of um, sine and cosine, or being able to get everything in terms of sine, everything in terms of cosine, one or the other, instead of just having two trig functions. But before I can do that, the only thing that I can do right now is really I have to um, work on trying to combine these fractions. So the way that I see to do that is to figure out your common denominator, because remember, when you add fractions, you have to have a common denominator. So the common denominator for this is going to be 1 plus cosine theta times sine theta. There's no other way to write a common denominator. That's the smallest function that both of these denominators go into. So that means I need that to be my denominator for both pieces. So I'm just going to rewrite that. And then I'm just going to keep that equals here because this is just coming down. I'm trying to get it to equal cosecant. So now what I have to ask myself is, what did I have to multiply this one by to make this denominator happen? And the answer is you had to multiply by this extra sine theta. So I'm keeping the original, and I had to multiply by sine theta since I did it at the bottom. And then for this other one, I have cosine theta up top already, but the question is, what did I have to multiply this by to get this denominator? I had to multiply it by 1 plus cosine theta. So then from here, when we go to simplify, the denominators are going to stay the same. Those won't change. But the numerators, you can simplify. You get sine squared theta. And then over here, if you distribute this, you get cosine theta plus cosine squared theta. And hopefully you're seeing this as I have a sine squared and I have a cosine squared. So if I rewrite this as one big fraction, meaning adding the fractions, remember the rule for adding the fractions, you keep the denominator and you actually add the top. So we have sine squared theta plus cosine theta plus cosine squared theta. And remember, these two pieces here are what I'm really focusing on. If I add those, or if we think about our property, sine squared theta plus cosine squared theta, it equals 1. So the sum of these two is going to be 1. So 1 plus cosine theta. So then on the bottom we have 1 plus cosine theta times sine theta. So then, since this is the entire numerator, we can cancel that with this. And when we're left with 1 over sine theta. So remember, all of these, I can keep carrying that down. And now we see 1 over sine theta. That's equal to, that's one of our identities from the front page. That's equal to cosecant. So I can just replace that, which is exactly what I wanted to prove up top here. So cosecant. So that one works out. So then just this very last one here, Again, we're trying to get one side equal to the other. It almost seems like to me starting with the right hand side this time might be easier because I don't really know what to do with the 1 over 1 plus sine theta. So starting with this seems easier because it allows me to simplify. So that's where I'm going to start. So first thing I see with this one is I have a secant squared. So secant squared, or secant is 1 over cosine. Since it's squared, it's the same thing as 1 over cosine squared. So I'm going to replace that. So this is 1 over cosine squared. And then tan I can replace. I'm going to turn tan into sine over cosine because I'm going to be getting cosine involved. So I want to make it as common to the other expressions as possible. So this is going to be minus sine over cosine. And then secant here is the same thing as 1 over cosine, which we talked about right here. So this you can replace as 1 over cosine. So then what happens is we can go ahead and we can simplify this. So we have 1 over cosine squared theta. Here, when you multiply across the top, you have sine theta. And then when you multiply across the bottom, you have cosine squared theta. So since I have the same denominator, I can go ahead and subtract these. So the denominator stays the same. Subtract the top, we get 1 minus sine theta. And then from here, if you look at what I'm trying to get out, I'm trying to get out something with sine in it. So that tells me I need to get rid of this cosine squared. So remember the relationship we have for cosine squared is the Pythagorean identity. So if I manipulate this so that I can replace cosine squared, that'll allow me to get everything in terms of sine. So I'm going to subtract sine squared from both sides. So I get cosine squared theta equals 1 minus sine squared theta. And then that'll allow me to replace this. So I have up top 1 minus sine theta. At the bottom I have, instead of cosine squared, I have 1 minus sine squared theta. And just like that other one, this is going to be a difference of perfect squares because it's a 1 is a perfect square and sine squared is a perfect square. So I end up with 1 minus sine theta on top. And then on the bottom, when you factor that, square root 1, you get 1. Do opposite signs. Square root sine squared, you get sine squared, or sine theta and sine theta. And at this stage, since the only thing I have in the numerator is 1 minus sine theta, I can cancel those. And I'm left with a 1 on top and a 1 plus sine theta on the bottom, which is exactly where we wanted to go with this on the other side. So if I carry that down, it checks out. So this was one way of going about this. You could have looked to see if you could have simplified some of the other things differently, like the secant squared. You could have replaced that with the Pythagorean identity. It really, and you would have gone a whole different way with it. And in the end, you should have got the same conclusion. Um, Another thing with this is the only thing that you're allowed to change from those set identities is this, like going from like the reciprocal identities to squaring each piece, because basically what I'm doing is I'm squaring this entire thing. If I square this, I square this, I also am squaring the 1. It's just when you square 1, it just stays 1. So that's why I didn't look like I did it, but I really did do it. So just keep that in mind. That's the only thing you can really change from those set identities, as well as rearranging any of the equations. And those are only true for the set equations. When you're trying to prove something, you work on one side and try to get it to equal the other.